number. Easiest example, 2 times 3 equals 6. So 2 is a factor of 6, right? 3 is a factor of 6 also. Just a reminder, the pieces of a multiplication problem are called factors. So the 2 is a factor here, the 3 is a factor here, and the 6 can either be called a multiple or the product. When we're playing around with factors, there's a few techniques we can throw at it. One is a factor tree. So this is just a quick review of stuff we talked about. Factor tree. And there's a couple of different ways to build a factor tree. The book goes over 2 of them. I talked about a couple of them in the last class. I like to use prime starting with 2 and working my way up, but there's lots of ways to do it. 2 goes into 6 3 times, 2 and 3 are prime, so I'm done. The ends of the branches on a factor tree tell me the prime factors of a number. And if I multiply all of those prime factors together, I get the prime factorization. 6 factors as 2 times 3. Oops, 3, there we go. And that would be the prime factorization. The other technique we apply with factors in a number are looking at factor pairs. And that's where we imagine making a rectangle out of 6. We could do it as 1 times 6 or 2 times 3, and we don't worry about flipping it to 3 times 2. And when I look at the factor pairs like this, then this gives me all possible factors of a number. So I can see all the factors of 6 are 1, 2, 3, and 6. I have all the factors there. Now, factors go hand in hand with multiples. We can't have one without the other. And so multiples are when we multiply. So it's just the result of multiplying. And unlike factors, where for any number there's a finite set of factors, for multiples they go on forever. So for example, oops, my pen got a little crazy there. Multiples of 6 are, well, 1 times 6, 2 times 6 is 12, 3 times 6 is 18, and then we just keep going, right? 24, 30, 36, and these go on forever. So 6 is the smallest multiple of 6, and again, when we're talking about factors and multiples, we're working with counting numbers, so we're really not going to talk about 0. 0 is technically a multiple of 6, but I just want to stick with counting numbers. So I have my first multiple, my second, my third, my fourth, my fifth, my sixth, and so on. All right, so multiples are the number or bigger, factors are the number or smaller, and we're working with counting numbers. So that's kind of a quick set of the basics so far. When we're working with bigger numbers than 6, things get more interesting. So let's suppose we try 360. It's big, but not too big. Let's do a couple of things. For 360, I would like to know what the prime factors are. And I would like to know what all of the factors are. So prime factors is where I work a factor tree. And I mentioned the other day, there's at least 2 different approaches. One approach is where you start dividing by 2 and then move up to 3 and then 5 and 7 working with primes. The other way is you just pick any pair of factors that work and then keep splitting from there. So I'm going to deviate from my normal practice here, and I'm going to say, well, 360 pretty easily looks like 10 times 36. The order you write those doesn't matter. And then we break down each of these numbers. Well, 10 could be 2 times 5. And 2, well, it's prime, I'm done. 5, it's prime, I'm done, right? We don't use 1 in factor trees. 36, one might look at that and say, wow, 6 times 6. Somebody else may differ and say, nah, I like 4 times 9 better. And that's okay. You can do either way. 6, this one is 2 times 3, and that one is 2 times 3. And every number, we keep going until we hit a prime. So when I get to the end of each branch, I should have just prime numbers at branch endings. And as far as the prime factorization goes, the typical way we write it is to put the primes in order, smallest to largest. So I have a 2 times a 2, so that's this one, and nope, there's another 2 there, and then a 3 times a 3, and the 5. If there's multiple of the same prime, we usually abbreviate that with powers. So I would write that as 2 to the 3rd power times 3 to the 2nd. And although I could write 5 to the 1st, 5 is simpler. So I'm just going to write 5. And the point is that should equal 360. So when you do a prime factorization, it's always a good idea to whip out a calculator to double check. So let's whip out a calculator to double check. So let's see, I had 2 raised to the 3rd power times 3 raised to the 2nd times 5. And computer agrees, yeah, those factors make up 360. And the cool thing about a prime factorization is if you ignore the order, there's pretty much only one prime factorization for any number. All factors is where we think in like rectangles. So what pair of numbers multiply kind of like length times width to give me 360? But we always write the smallest one first. At least that's my recommendation. And start with the simplest one, which would just be 1 times 360. So 1 times 360. And then I try 2, and 2 is going to work because it's even. 2 times 180. And a calculator can be handy here if you need one. 3, let's see, 3 goes into 36 12 times, so that would be 120. And 2 went in, and the result is still even, so I believe 4 will go in. And maybe I need a calculator sometimes, maybe not, depends on the day. 4 goes into 36 9, so that should be 90. Let's see, it ends in a 0, so 5 should go in there. And let's see, 5 goes in there how many times? I think 72, half of 72 is 36. Yeah, that looks right. 6 goes in there definitely because 6 goes into 36. So that should be 60 times. 7, I don't think so, but that's when we would have to check. So whip out a calculator if you can't do that in your head, and my head isn't working on that today. So 360 divided by 7 gives us a remainder. So that one's out. 8. So let's see. 4 went in, and the result is still even. So that means there's another 2 living in there. 2 times 4 is 8. So let's see. If I cut 90 in half, that gives me 45. So it should be 8 to 45. Did that trick make sense there? And unfortunately here on this computer, it's hard for me to see the chat. So you might need to voice to me that there's a chat if I don't see it. How are we doing out there? All still with me?
Yep.
Okay. And I think the problem is on this computer, when I bring up the chat, it blocks the screen from your video. Do you see a blank white box in the middle? Or does it look okay?
I see like a black box in the middle.
A black box, okay. Yeah.
I do a black box too.
Yeah, that's the problem when I try to have the chat window open. I got to figure out how to resolve this. I have 2 problems on this computer. One, if I bring the chat up on the same window that I'm recording, it appears as a black box. And 2, if I try to go to a double screen, it messes up the magic tablet I use to write with. I haven't figured out how to fix both those problems yet. All right, so bear with me. So if a question comes up, you might have to voice it and say, hey, read my chat. All right, so let's see, where am I? 8, I believe, is 45. 9 should go in there because 3 plus 6 is 9. 40 times? 9 times 4 is 36. 10, I saw that one earlier. 10 times 36. Uh-oh, I'm running out of room. I'll have to come up here. Let's see, 11, I don't think so, because 11 goes into 33. 12, yeah, I think 12, if you look at the line with 6 times 60, 60 is even. And if we pull the 2 out of the 60, 2 times 6 is 12. 60 divided by 2 is 30, so it should be 12 times 30, which makes sense because 12 times 3 is 36. 13, I doubt it. 14, I know, because 7 didn't work. 15, because 5 worked, 15 might. So let's see, I can't do that one in my head. Oh, I can I? I think it's 15 times 24, is that right?
That's what I got.
Oh, good, thank you. And I'll just explain how I came up with that without a calculator. In my head, I was thinking, well, I know 15 goes into 30 here. So I was looking at this 30 and thinking that is 2 times 15. So if I take that 2 and multiply by 12, 24 should be the other factor. Okay, so I was just kind of playing around with factors. 16, let's see, 8 went in and the result isn't even. 8 is 2 times 16, so I don't think 16 will work. 17, I doubt it. We'd have to check on a calculator. Can someone check 17?
No.
Doesn't work, okay. 18, I believe, does work because 9 goes in and the result is still even. 9 times 2 is 18, so I think it's going to be 18 times 20. 2 times 18 is 36. Yeah, that seems to work. And then I doubt 19 is going to work. And then I'm at 20, so I think I've got them all. Oh my gosh, that's a lot of factors. Oh, yeah, okay. And to know you have all the factors, that's a much harder problem to solve. The prime factorization is pretty easy. You multiply the prime factors and it either works or it doesn't. Finding all factors is a bit trickier, but we think we have what? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 different factors. Wow, 36 is a rich number. That's amazing. I think it's amazing. Pretty cool. So it looks like there are 24 different factors. And actually there is kind of a way to check, and I think I'll show you this. I usually don't present it, but it's kind of cute. If we consider that 360 is equal to the prime factors 2 to the 3rd power times 3 to the 2nd power times 5 to the 1st power, when all of these other factors over here, like the 120 and the 90, let me get a highlighter here, like 120, 90, 72, any factor in this list right here, because 360 is only made up of these prime factors, all of these other factors can only come from a combination of 2s, 3s, and or 5s, okay? And it could be, right, a 5 might not be present. For example, 5 doesn't go into 72. So that's just made up of 2s and 3s, right? So I have 3 2s to work with. I have, let's see, now did I get the right? Yeah, 3 2s to work with, 2 3s to work with, and 1 5. Now, however, it's actually more than that, because these 3 2s right there, I could use 1, 2, 3, or none of them when I make a factor. So as far as options for use here, so options for using these prime factors, For the 3 2s I have up here, I could either use all 3 of them, 2 of them, 1 of them, or none of them. So that gives me 4 options for using those 2s. For the 2 3s I have here, I could either use both of them, 1 of them, or none of them. And that would be 3 ways to use the 3. And there's only 1 5, so it's either there or it's not. And that gives me 2 options. So if I take 4 options times 3 options times 2 options, what does that give me? 4 times 3 times 2 on a good day is 24?
24.
Yeah, and how many different factors did we find?
24.
24 different factors. So it turns out there is a way to check. It's a little bit complicated as to why it works, but it works just because either the prime factor is there in the other factor or it's not. And then it depends on how many of them. So if I know the prime factorization of a number, all I have to do to guess at how many factors there might be is to just take the power and add 1, right? 3 plus 1. Take the power and add 1. 2 plus 1. Take the power and add 1. 1 plus 1. And then if I multiply all those ways of using the factors above, that gives me the total number of options in the end. So there should be 24 factors there. So I'm just going to test that theory again here on the number 6, real simple one. We know that 6 is equal to 2 times 3, which is 2 to the first times 3 to the first. So if I want to use that to consider the number of factors total that the number can have, the 2 is either present or not, so that's 2 ways to use it. The 3 is either present once or not, so that's 2 ways to use that. 2 times 2 is 4, so there should be 4 different factors of 6. And then we could seek them out if we wished. And we know that they are 1, 2, 3, and 6. Yeah, I almost said 4, that would have been dangerous. Okay, so review of what we did with a slight extension. Let's see, I guess we're now ready to move on to greatest common factor and lowest common multiple. Just want to wave hello again.